Yeah, so as Shangyan said, I'm going to give a very brief introduction to Feynman diagrams. And so Feynman diagrams are sort of a very nice way to represent the very complicated calculations that you get from quantum field theory that we use to make predictions about events that we see at collider experiments. And it's really a nice tool because I said it allows you to do, or at least allows you to show very complicated math with very simple pictures, and allows almost everyone, including us experimentalists, to understand what physics we're looking at. And this is sort of why I gave the subtitle to this lecture as QFT for Dummies, because that's really what it is. And so I don't want to touch on any of the math that goes into turning the Feynman diagrams into equations, or even more calculating them, because it's quite complicated. But I will try to sort of highlight the buzzwords that are related to it that you can come up in your undergraduate career, most likely in upper level classes. Right, but anyway, so as you can imagine, sort of the underlying part of Feynman diagrams is quantum mechanics, right? That's basically what we do when we study particle physics. And the specific part of quantum mechanics that the Feynman diagrams try to touch on are path integrals, right? And this is the idea that to get from state A, which let's say in your case are the initial particles in your collision with certain momenta, to state B, which are the final particles that come out of your collision, the way to get or to calculate the probability of getting from state A to state B is just to sum up all the possible paths that physics allows for to get from state A to state B, and just sum them all up, right? And this is just, it's very general to quantum mechanics, right? And of course, all the paths through the physics space, you just weight them by the likelihood that can happen. And then those are the equations that go into that. And the second thing that you need to know from quantum mechanics is the idea of amplitude and probabilities. So an amplitude is just a calculation that, given final state A with initial state B, and so I think I sort of mistakenly reversed the letters here, but anyways, to go from state B to state A with physics H in between, as I tried to show using what is called this bracket notation, the things between the arrow brackets, that's the amplitude. But the actual probability of the transition is the square of this amplitude. And one more thing that I'm showing here is to go from probability to cross-section, you just have to stick this probability into an additional formula.
Wait, sorry, really quick. So what would like A and B, like what would be an example of an amplitude in physics?
Sure, I'll try to show some examples later on once I show the Feynman diagrams, but you can think of, let's say, B, the initial state, as two quarks with certain energies before a collision, right? And A being whatever final state that comes out of that collision that you're interested in. So but I'll show that.
Would it be like that? It would be the energy, or is
yes,
it because
energy, particle multiplicity, and particle types.
Okay, thank you.
And that's at least related to particle physics, right? Quantum mechanics is used for other types of physics too, and in those cases, you can have other sort of definitions of initial states. But for particle physics, especially when it comes to Feynman diagrams, it's the particle multiplicity, type, and energy. Okay, quantum field theory, that's the next buzzword that's relevant to the mathematics. And quantum field theory, it's basically what happens when you combine these quantum mechanics with special relativity. The special relativity just adds sort of special conditions on how you can perform the calculation such that you don't violate basically time. Right, and QFT is really, that's the framework that allows us to calculate predictions for the Large Hadron Collider and other collider experiments. Right, it sort of gives you the probability that a process will occur. Of course, I should put the probability in quotes. In the end, what we call is something related to probability, which is a cross-section. And there are, let's say, two, not flavors, but sort of subsections of QFT called quantum electrodynamics, QED for short, which deals with calculations related to the electroweak force. And you have also quantum chromodynamics, which relates to calculations that deal with the strong force. And just because the types of particles that are the propagators for these two types of interactions, they result in different math. So sort of different ways of solving the equations are needed. Okay, so now to actually, what are these Feynman diagrams? Right, so Feynman diagrams, as I tried to allude earlier, they're just pictures that represent very complicated calculations. So here I'm just showing a picture of an interaction, right? And the way to interpret them is that on the x-axis, you have time, and on the y-axis, you have basically position, right? And the way to interpret it is that you have the two initial particles, in this case, an electron and an anti-electron. As time goes on, they meet, they collide, and they produce a photon. And then after some time, that photon decays or turns into a quark and an antiquark. And then at some point, one of those antiquarks, it radiates a gluon. Right? So, and in this case, your final particles are the quark, antiquark, and a gluon. Right? And this is, I would say, a very easy way to show this is the physics I'm looking at. I collide two electrons to look up for two quarks that come out with a radiated gluon. So some of the terminology, apart from initial and final particles, that to look for is vertex. This is just another type of interaction. And a propagator. This is sort of a particle that happens somewhere in the interaction. I'll talk more about both of them later, but the main thing I want to highlight is that only the initial state and final states are, in quotes, real, right? Anything in between, it's a virtual particle. So it doesn't necessarily have to follow the rules of energy conservation. Right, and in quantum mechanics, right, this is kind of related to the uncertainty principle, where you can always trade between momentum, borrow some energy for some momentum, and then return it back.
Wait, quick question.
Yes.
So the positron on the left, why is it going away from the collision rather than towards it?
I'll get to that soon, but it's just a formalism to tell quarks and antiquark. Particles and antiparticles apart.
I see.
Okay. Yeah, Feynman rules. So Feynman rules. So these are just rules for how you can draw those diagrams. And any diagram that you can draw by following these rules corresponds to an actual physics process that can happen. And so you sort of can think of these Feynman rules as just Lego. Building blocks in Lego that you can put together in any way that you think is possible. And I'll show you some examples of Feynman rules on the following slides that correspond to the standard model. To generate the list of, look at the theory Lagrangian equation that sort of describes, and I'm not going to show that here, but it's the Feynman rules from that. It's not only building blocks that are part of the rules, but it's also a convention how you convert to the integral. Okay, so what are the rules? For particle types, these are all the possible particles that you can have in the standard model, or particle types, right? If you have a quark or a lepton or a neutrino, which I think you also classified as a lepton, you just draw a solid line. Of course, for quarks, for all these particles, you can have that particle and an antiparticle. And the way that you indicate if it's a particle and antiparticle, as I referred to earlier, is by the direction of the arrow. If the arrow is pointing in the direction of time, it's a particle. And if it's flowing in the direction opposite to time, it's an antiparticle. And this is sort of particles and antiparticles, right? Once you write down the integral, they just come with slightly different rules for writing down the integral. And that's why you have to be able to tell them apart. You also have gluons, which you show with these curly lines with the loops. You have a Higgs boson, which is just a line with dashed things. And you can also have the electroweak force carriers, right? The Z, the W, or the photons. And those are just shown as the squiggly lines. And quite often, because a certain type of line, while it corresponds to a certain type, which gives you the rules, you always also want to sort of label them with a letter to just say, what actual, not a type, but flavor it is, to indicate what values certain constants have to take, right? So for example, for a quark, you sometimes might want to say it's a bottom quark because the bottom mass does go into the equation. Okay, so those are the particle types. The other key is are the vertices, right? And so here is again just a summary of all the possible vertices in the standard model. Sort of on top, you have the vertices that are related to the strong force. So basically anything to do with the gluon interaction. Then on the next row, or actually next two rows, you have interactions that correspond to the electroweak force, right? So you have interaction of fermions with a photon, and also interaction of fermions with a W or a Z boson. And at the bottom, you have interactions with the Higgs boson, and also some self-couplings. And so one thing to say is that these are sort of your basic building blocks. These are the Lego blocks that go into making Feynman diagrams. And you can rotate them and connect them in any way that you want, right? So for example, the diagram that I showed earlier, I'll just go back to it. And just show it here so you have it for reference. Right, this diagram, right, it's a combination of this vertex with this vertex repeated again, but with gluons, with quarks instead of electrons, and also the radiation comes from this vertex, right? So this diagram at the bottom here, it's just joining the these three little building blocks together. Okay. So another thing to sort of point out is, so that's how we make the Feynman diagrams. Now I just want to sort of give you some idea how to interpret those final diagrams to make some very rough estimates for what the physics will actually look like. And so one idea is off-shell versus on-shell particles, right? And this is what I mentioned earlier, is that anything that is not an initial or a final state particle is a virtual particle. It's not real. So it can violate rules of energy conservation. However, violating those rules comes at a cost, which means that the probability of that happening is smaller. And then there's just sort of a hint in the math that happens, is that when you write down the rules, just to give you a bit of a taste, is that this Z that's in the middle, it's the sort of the way it shows up in the integral, it's called the propagator, which has this form. And so what you can see, it's basically 1 over something, and where that something is k, which is the momentum of the input particles that you put in, minus the mass of the z, plus a higher order correction, which is this I epsilon, right? And if your k is equal to mz, right, when the input momentum is equal to the z boson mass, right, which is basically energy conservation, this will be as 1 over 0, right? So it goes up, it explodes, it's preferred. However, that equation is also valid if the input momentum doesn't match the z mass, but that value, it will be 1 over some physical value, and that value will be larger the further you are away from the z mass, meaning that the actual fraction will be smaller. That just means it's suppressed. And I think a very nice way of seeing this in the real world is, I would say this is the most famous result from the lab experiment. So the lab experiment was the predecessor of the Large Hadron Collider. It was in the same tunnel, but instead of colliding protons, it collided electrons. And for a reason I'm not going to get into in this lecture is that the way you run an electron collider is that you have to specify explicitly what mass or what center of energy, what is the center of mass energy for the electrons that you run your collider at, and then you scan the energy. You take several points, right? And the center of mass energy is basically this k in the equation. And you can see in this is the closer that you get to the z mass, which is around 90 GeV, the number of events there goes up. And the further you get away from it, it goes down. And the other thing that's also nice is that the width of this peak, if you're not limited by the detector resolution, is actually proportional to this 1 over IE. So it allows you to actually measure these higher order corrections, which could potentially also point at new physics. Right, and the other thing I wanted to say is that when you're operating your detector is sort of in conditions where you're producing events at this peak, you call this a propagator, this virtual particle on shell. And if you're off it, where you're not following energy conservation, you call it off shell. Okay. The other thing that you should know about Feynman diagrams is that loops are allowed, right? When I said that you have these little building blocks and you combine them any way you want, that also means that if possible, if you can make loops, well, those are then allowed. And I show 2 examples of, I think, 2, I would say, fairly famous loop diagrams. In the left is gluon-gluon fusion. This is where you take 2 gluons and you collide them. And as a result, you produce a Higgs boson. This is actually when we make Higgs bosons at the Large Hadron Collider, this is actually the most likely method of producing Higgs bosons, which is actually quite funny because, right, you think of Higgs boson as, I guess you'll learn more about this in the next lecture, you think of the Higgs boson as, that particle that gives mass to other particles, right? Or put it another way, it interacts more strongly with particles that are massive. However, a gluon does not have mass, so it should not interact with the Higgs boson. But because of these loop diagrams, you do have a way of producing the Higgs bosons from gluons. And the other, I would say, fairly famous Feynman diagram is this one. It's called the penguin diagram. The reason it's called the penguin diagram is because a bunch of theorists got high at CERN and made a bet if one of them can put the word penguin in the next paper, and this is what they came up with. But other than that, it's actually a very important process because it's useful for studying CP violation. The other thing I want to mention about loop diagrams is that they're actually very difficult to calculate. Mainly because if you just write down the integral and integrate it, what you get is a result that is infinite. right? Which you at first think that's okay, that's not physical, but it turns out the reason it's infinite. Well, the reason it's actually physical is that to get, to actually to do the physical calculation, you have to thumb all of the diagrams that have the same initial and final states. Right. This is the idea of, you have to take into consideration all possible paths, and that includes loop diagrams that have 2 loops, 3 loops, and 4 loops, and so on. And what happens is that if you include all of the possible loops, is all of these infinities, some are with plus signs, some are with minus signs, they end up canceling to actually give you a physical answer. Of course, the problem is that calculating all possible loops, right, because you can have infinite number of loops, it can get very difficult. And so for that reasons, theorists have come with a method called renormalization, where they say, okay, my calculation is, it's infinite, but there's a cancellation that makes it finite, and I'm just going to pretend that I know that result at a given energy, and then do mathematics that tells me, okay, if I change energies, how does this cross-section, or how does the result change? Yeah, this is called renormalization. Okay, the other thing that I think is worth mentioning is the order of calculation. These are just some terms that you will see when you're presented with Feynman diagrams. And this is to just say, right, not all possible diagrams are always included in a given calculation. And that is just a computational statement, right? In theory, you have an infinite number of diagrams, and if you were to calculate them all, that will take a lot of resources, especially if they contain loops, which are very difficult to calculate. And so for that reason, you just say, okay, I have different orders of calculations, different different accuracies. So some names are tree level. This is just a diagram which does not contain any loops. And again, this is quite easy to calculate. Then you also have something called a leading order diagram. This is the lowest number of vertices that is required to draw a diagram. In most cases, it is just a tree-level diagram, but that is not always true, with example being the gluon-gluon fusion Higgs production, which I showed earlier. Because the Higgs doesn't directly interact with gluons, there is no tree-level diagram. Instead, you do produce it. You have to produce it at loop level, and that is the lowest order there. And then you have next to leading order calculations, where next to comes with an exponent, and that exponent just tells you how many extra vertices you're allowed to draw, right? So in most cases, our calculations are to next to leading order, although a lot of processes over the last few years have become available at next to leading order. And just sort of, and also quite often because the vertices for QCD and QED, they have different orders of magnitudes. You count and different ways of calculating them. You count those orders separately. So quite often you would say my calculation is next to leading order in QCD, but only leading order in electroweak. And so just sort of give you an idea what I mean by leading order versus next to leading order. For fermion production at an electron collider via Z boson, what I'm showing here, the diagram on top is leading order, because here you draw it using 2 electroweak vertices, and then the next to leading order is the diagram at the bottom, where I just inserted a loop in the middle. Right, and in this case, you have 4 electroweak vertices. Okay, so the other thing is you quite often have different types of diagrams that you can come across. And this is not necessarily the complication in calculation, but it also gives you a sort of a mapping to sort of a more classical way to think about what process you're looking at. For example, in the left, you have what's called an S-channel diagram. This, you can also think of it as a production of a particle, right? P1, P2 collide. They make this dashed line, and then dashed line decays. You have a T-channel, and this is, you can sort of think of it as scattering. Which your case, P2 particle, is just hanging around somewhere. P1 comes zooming by. It interacts via some kind of a mediator, maybe a photon, into the case of the electric force, and they just scatter off top of each other, go along their way with some change in momentum. And then also you have a U channel, which is similar to T channel, but the particles change positions. This is actually a very nice way to, this is a bit of a sidebar, but so it's a very nice way to think about also different experiments that are trying to, look for new physics. In this case, dark matter searches. And this is a simplified model. For example, if you look at the left diagram here, the chi is a new particle that you think is the dark matter particle, and the Q is quark, or something that's some standard model particle that you handle on. And the idea is that these two they interact together using some kind of a mediator, a new particle called phi. And then let's say if you just focus on the S-channel diagram on the left, the way that you look at it, how you rotate your head, it gives you a different experiment, right? So if you assume that time flows, along the y direction and up, right? That's a collider experiment, like the Large Hadron Collider, right? You have two quarks that come along together, they collide, produce a mediator, and the mediator then decays into two dark matter particles. Now, if you take the same diagram and look along the x-axis, you pretend the time is there. That is a direct detection experiment like LAX, right? The idea there is you make a big tub of some material. I think now they're using liquid xenon, and what you do is you just wait and keep looking at this liquid xenon, and you just wait, and you hope that at some point a dark matter particle will come by. It will recoil of your xenon atom, and then that new energy in the xenon atom will result in some light that you can then detect. Right, and then the last axis, if you look at the y-axis looking down, you have indirect detection, right? This is for experiments in space like AMS, where you hope that somewhere out there in the universe, you have two dark matter particles that come along together. They collide, produce this mediator. The mediator then decays into standard model particles, hopefully with a lot of energy, that then comes, and then these standard model particles then come to your detector, for example, AMS, and then you see that. Oh yeah. Okay. So that's all with that sidebar. The next thing I want to talk about is interference. This is how you actually sum these diagrams and turn them into a probability. And so, as I mentioned earlier, you have to take all possible paths, which means all possible diagrams that give you your result at all orders of magnitude. In this example, right, you have a leading order diagram, which is a tree diagram. Then you have a next to leading order diagram, which has one loop in it, and then the dot 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 corresponds to even more loops in your diagram, right? So to get a probability of an interaction, you have to add up all of these possible diagrams. And that's not only that, that's just the amplitude. To get the probability, you have to square that sum, right? And when you square a sum, you get different cross terms that you combine. And the resulting equations ends up looking like this, right? You have your leading order tree level diagram squared. Then you have your the first one loop order diagram squared, and then you have the product, of these two, the leading order and the next to leading order diagram. And when you're sort of mixing these terms, that's something that we call interference terms. And the way I wanted to show this is it shows you sort of the sort of hidden subtlety of doing these calculations, which is you cannot just calculate a single diagram and then hope to add it, linearly with other diagrams. So one person calculates the, let's say, the tree-level diagram, another person calculates the one-loop diagram, and then, on Friday you meet for lunch and you just add them together. That does not work. You have to also consider these cross terms. And one thing that happens in these cross terms is that sometimes how the signs work out, this amplitude can either be positive or negative. So these interference terms can sometimes enhance or enhance, reduce the number of events that you expect. So they are important. Okay, and the other thing I sort of wanted to show in this formalism is that the more vertices that you have, one of the assumptions in quantum field theory is that the size of the vertex is less than 1, much less than 1, which allows you to do an expansion, right? Or put it the other way, anytime you add an extra loop diagram, its magnitude will be smaller and smaller and smaller. So you can try to do approximations just by removing or just not including those diagrams in your calculation. Okay, and I think this is the last page I want to show on Feynman diagrams, which is MadGraph. So as you can imagine, right, Feynman diagrams are this nice framework for just building up any physical process that you can and then calculating it. And then you can think, well, if there's a fixed set of rules, can I just write a computer program, given I have an initial state and a final state, computer give me all the possible diagrams that go into it, and then actually write down the integrals and do the calculation for me. And yes, and if you ask that, yes, it's possible, and that's what theorists have done quite a long time ago. And the result is this program called MadGraph. Right, it's freely available. They put a link to the website. You can go there and download it. And it's also very easy to use, and it allows you to do predictions very fast, right? And I just put an example here, where I say, generate proton-proton collision. Here, by proton, I mean just do all possible combinations of quarks, antiquarks, and gluons that you find with the proton, and get me all the diagrams that result in two jets. Right here, a jet is sort of defined as either a quark or also a gluon. Right, and then it does its magic. It draws all the diagrams. It puts out a very nice web page, right, that you can look at. I uploaded the result of this command here, and here I just put some pictures that you can see. Right, this is all the diagrams that give you the interactions between an up quark and a gluon, and that result in an up quark and a gluon. So you get all the diagrams that way, and if you actually want to see the cross-section, you just say launch. You can tune some settings to say, I'm at a hadron collider at this given energy, generate this many events, and so on. But the defaults are usually quite sensible. And yeah, once it's done with the calculation, you get a nice table like this, which tells you at a 13 TeV proton-proton collider, the cross-section for digit events is 7 × 10⁸ picobarns. You also have in this case, 10,000 generated events that you can look at, plot their distributions, and so on. Yeah, so I think that's all I've prepared. So I don't know, are there any questions?